Thanks a lot for joining me. This is a hands-on session on the Orchidea software for assisted orchestration. And during this lockdown, as I was saying, it was kind of strange to do work and research and teaching. So I thought maybe to get in touch with this community would be fun and interesting. And I will give you a quick overview of the system, of the story of this project, and on the tools. The main reference page is this www.orc-idea.org is where I deploy the software and the system and the information. You can download the software here. You can download the data sets that you need to use Orchidea here. And there are links to other pages, such as the YouTube channel. So we have a YouTube channel that is growing now, is called Orchestration Idea. We have at the moment just 3 tutorials, but we plan to add more tutorials in the next few weeks, among which this talk that I'm giving now. So please subscribe to the channel, let us grow the channel, and this will be helpful. In order to run Orchidea in the Max environment, you need some few extra packages, namely the back libraries. There's a website, it is backproject.net, in which you can download all the libraries that are related to this project. It has been developed and maintained by Andrea Agostini and Daniele Ghisi since a couple of years now. So basically what you need is all the 3 libraries, back, cage, and data. You don't really need to use Orchidea. Orchidea is independent from these packages, but you need these libraries to show and to plot the solutions if you are interested in plotting the solutions too. Okay. I just want to point out that we have a forum web page on the IRCAM forum on Orchidea, explicit on Orchidea. So there are a number of threads of people that can ask questions, and I do my best to answer to these questions. And this is also in the forum, and it's also in the forum that you can download other extra data sets like Orchidea Sol or Full Sol that are more large and extended version of the database that ships with Orchidea that is called TinySol. So to recap, when you download the package, the Max package, you download also a small data set called TinySol. It is being extracted from Sol. It is a Studio Online library developed by IRCAM a number of years ago. And these small data sets only include Ordinario playing styles. So it's roughly 1 gigabyte. But you can still do some quite interesting things just using these simple data sets. But if you need more data, as you should probably at some point, you may want to download Orchidea Sol and Full Sol. So Orchidea Sol is an extended...
Here, TinySol 2020 is actually TinySol.
Yes, so TinySol 2020 is a review. So we renamed... Sorry?
On this link. It's not TinySol 2020, it's TinySol.
Yeah, so the point is that we just renamed TinySol in 2020 because we are in a process of reviewing the files in these databases because there were some mistakes in the files. So I think there will be versions of these, so you may want to check the latest version. But the one that you have in Orchidea, normally it should be the TinySol 2020, that is the latest revision of this TinySol dataset. I was saying that Orchidea Sol is somehow the starting point for you when you are a bit more skilled in using Orchidea, and is a subset of Sol again, but this includes also several playing styles, and is, I don't know, I suppose it's roughly 8 gigabytes, so it's pretty big. And then when you are really ready, you can go to the Full Sol that is not free and requires a premium subscription to IRCAM Forum. That is the full Studio Online. But we did some work in order to improve the dynamics of this file. So there will be an upcoming paper about the work that we did with Daniele Ghisi on how we improve these recordings for the matter of assisted orchestration. I wanted to just start with a series of slides so that I can give you somehow a context of the project. This is my own perspective, guys. So just think that this could be somehow not totally shared by all the community behind Orchidea, but it's just an overview, okay? So I think it would be interesting to at least give this overview. So a few disclaimers before. The first disclaimer is about me. So if you don't know me, my name is Carmine. My world is in between these three things: mathematics, music, and creative computing. And Orchidea is a good fit for me in the sense that you need to have some knowledge and expertise in music, like composition and orchestration. But at the same time, you may want to have some knowledge in mathematics and how you model these using computers. So I am now an assistant professor at Berkeley in the music department, and explicitly I stay at the CMA, the Center for New Music and Audio Technologies of the University of Berkeley. So feel free to reach out anytime. Now, the other disclaimer is I will not teach you orchestration today. Okay, so I assume that you know how to orchestrate, and this is an important thing for me. We don't with Orchidea, we don't orchestrate for you. We help you orchestrating. So it's a different thing. Like you should always see these kind of tools as assisting tools. In fact, that's why I like this expression, computer-assisted orchestration. So we help the composer to orchestrate. This means that basically you should see Orchidea as a calculator, as a computer, something that speeds up your calculations, and not something that replaces your own fantasy or creativity in a sense. So that's just to be sure that we are on the same page. Now, let me give you a quick overview on the problem of assisted orchestration. So we can start with a preliminary definition. So the process, so assisted orchestration can be seen as the process of searching for the best combinations of orchestral sounds to match a target sound under specific metric and constraints. Well, I don't see this as a very useful definition. So, but this is correct. This is somehow what I think is assisted orchestration, but I think we need some context to understand better this definition. And so I start with always this sentence by Jan Maresch, that is from a paper that he wrote in 2013 called On Computer-Assisted Orchestration. But basically he says, in 2003, I presented to IRCAM a proposal for a long-term research project on the subject of computer-assisted orchestration. The results of this research project led to the prototype software Orchidea. So basically, he says that this thing started somehow, some more or less officially at IRCAM in 2003. And in fact, since then, many things happened. You know, it's a long-standing problem for IRCAM, so it has been researched for more than 15 years. And this led to the development of many things, such as MATLAB frameworks, MaxMSP's interfaces, C++ tools, and so on. And also it generated a lot of, research like PhD theses, Grégoire Carpentier, Damien Tardieu, Philippe Esling, and many and several papers, like among which journal papers. But I want to stress the fact that this project has been made by many composers. So I know that many of you that are listening to this talk have been part of it. So I've been involved to some extent to this research. Basically mainly through the work group on assisted orchestration that IRCAM had for several years, from 2004 to 2011. And I see many of you, Jean-Baptiste Barrière, Louis Naon, and many others, so that are listening to this talk. So it's nice for me to see you there, guys. And I just want to say that this is a community-based project. So it's a project that, of course, had the privilege of being funded by important institutions such as IRCAM and Haute École de Musique in Genève. I will talk about that later, but is basically also a project that is made by people that discussed past years in testing tools, proposing ideas, and sharing ideas. So this is a very interesting thing for me. And when I'm in the project since several years. I was a user of the first tools, and then I am now somehow a developer of the tools. So I'm interested in this project for several reasons, for several personal reasons. So I would say that the basic idea behind the assisted orchestration is that we want to make connections between the symbolic space of scores. So music can be seen as a bunch of symbols, right? So like notes, pitches, instruments, and durations. But at the same time, music can be seen as something that exists in the signal space, like timbre, like a raw sound file. So the idea is that assisted orchestration can be the link between these two, can make connections between the timbre space or the signal space and the symbolic space of scores. And this is a kind of an interesting connection for composers, right? Composers, especially since, I don't know, in the past 20 something years, are very interested in the acoustic space of composition. So there are many composers that now are mostly interested in sounds and less in notes, if you see what I mean. And well, if I just to name a major thing, I refer to spectralism, in which composers were more interested in music as spectra than traditionally discussed as chords or basic harmonies, if you see what I mean. We will go through that later in a second. So I thought I would do a sort of history of assisted orchestration. I'm not at all a musicologist, so I definitely made mistakes, but just stay with me for a second just to have a rough idea of the steps, of the stages of this thing. So I put on the left, grayed out a sort of ante litteram moment in which composers didn't really know that they were going towards assisted orchestration, but they had some intuitions. Basically, they started thinking in a I don't know, in a way in which the sound and the spectrum would be more important for them. I refer, for example, I think when I say that, I think about some music by Xenakis, for example, like Metastasis, or even Atmosphere by Ligeti. So these kind of things are not related to assisted orchestration per se, but are somehow the seminal ideas, in my opinion, that motivated this kind of thinking. Then I would say there was a stage, this is an early stage of the process, that is a stage in which composers wanted to somehow use computers to speed up orchestration, but they couldn't really do that. And so they did that by hand. So basically they did a manual analysis on the sounds and they took decisions given this analysis. And I have, there are important examples in this kind of moment, among which Mortuo Splango Vivos Foco by Jonathan Harvey, or Partiel by Griset, and many others. So guys, I'm sorry if I don't name all of you. I know that you are have been involved to some extent, but just to give a rough idea. And then there are the last two stages that are officially assisted orchestration, meaning that we have tools to use to assist composers during the orchestration stage. The first period that officially I see it starting in 2008 is with Orchidea and Orchis, these two tools that were for static assisted orchestration. Static meaning that you have sounds that are not changing in time and you orchestrate these sounds. A major outcome from this period was the piece, again, by Jonathan Harvey, Speakings. There are papers on this piece that explain what they did. And Gilbert is here, and he was part of it, so he can maybe adding something later. So, and then I see a second period of this assisted orchestration research that is about dynamic assisted orchestration. And I think it started in 2013 with Orchids. Orchids is the first interface basically done by Philippe Esling and Daniele Ghisi, in which time was addressed to some extent. So they were able to use time series and to match time series in order to somehow mimic the temporal evolution of sounds. There were problems in using these tools for some, kind of optimization problems, but it was an interesting idea to me. Then I put into this thing also Orchidea, that is the latest generation of these, tools that basically was born in 2017, in which time is addressed in a somehow different way, like more on the onset level. So it's more a macro level of time, and this we will see clearly during the talk today. So this just to give you a brief overview on these complicated and complex matter. So I was saying, let me give you a few examples for the ones of you that are not aware of that, of these works. So the first sound that we associate to assisted orchestration somehow is the bell in Jonathan Harvey's Mortuo Splango Vivo Svoco. I'm not sure, I think I should share the audio. Sorry guys, let me share again the screen because I think I'm not sharing audio here. So give me a second. Yeah, no, I share this computer sound.
We did hear the bell. Huh?
Yeah, okay, but if I share audio, should be more clear. Let me try again, guys. Anything better? Okay, did you hear, guys?
Yes.
Cool.
Yes.
So there is an interesting comment by Curtis Rhodes about Mortuo Splango Vivo Svoco, saying that this is somehow the first time that IRCAM did something that was not exoteric and actually appealed to a wider audience. That's fun for me to see this kind of a comment, you know. So I just named this piece as a reference, okay, guys? So it's nothing more than a reference. So it's something that somehow motivated the research. So basically in this piece, Harvey tried to transcribe the sound of the bell and reconstruct that by synthesis. And so this transcription has been done manually at the time. So you would take the sound, you would analyze the partials, you would analyze the temporal decays of the partials and these kind of things, and then you would replicate that with some sort of synthesis systems. But then I would like to mention another piece that is Metal Extensions by Jan Naresh, in which basically the idea behind this piece was, he wrote a previous piece called Metallics, in which he used electronics and trumpet. And then he wanted to make a sort of transcription of this piece for instruments. So the idea that you can transcribe electronic sounds to instrumental sounds is somehow related to assisted orchestration. So you would, again, analyze the sound, you would transcribe the partials, you would transcribe the temporal evolution of these partials, and then you would, you know, make an equivalent of these sounds using musical instruments. If I put these together with the idea that is behind Partiel by Griset, this idea of instrumental synthesis. So you make a sound synthesis using musical instruments. That's an interesting idea. But, you know, to some extent, this is very difficult because by definition, an instrument is a synthesis. So when you put isn't a complex object that you want to use as a building brick for a sound synthesis. So it's not easy to make instrumental synthesis. But these are just, you know, point de repère, so some sort of, you know, references that I want you to know before we start. And then again, finally, this 2008 piece by Harvey Speakings, that is an example in which the composer used Orchidea at the time to sonify the human voice. And they also did many other techniques during this piece, like cross synthesis and many other things. And so it's a monumental piece, a masterpiece for me. It will be in the history of music, in my opinion. So I think this is worth mentioning in this discussion. So these three stages, I would say the Mortuo Splango Vivo Svoco, and then Metal Extensions, and then Speakings, are representatives of the early stage in which the analysis was done manually, then the first stage in which now the analysis is done in a static sense by Orchidea. So if I should define this problem, I would say that when you write a score, you just basically write symbols in a page, and then you play the symbols and you generate sound, and this sound lives in the timbre space. So the problem is, given a sound, can we retrieve the score? That's the way we can see assisted orchestration. But be careful, this is not transcription. Meaning, for example, suppose that the sound is a piano playing and then you want to retrieve the score. This would be transcription. But the sound that we have in this signal space can be any kind of sounds, like bells or, you know, cars or voices, in which you have not a score in the first place that generated these sounds. So that's a sort of I would say general case of transcription. Okay, so this is somehow the way we can see a way that we can you know, use to imagine assisted orchestration. But if I should state the problem in a better way, So we can say how we can use an orchestra to reproduce a target timbre within a compositional context. So in other words, how we can best match a sound, given target sound, by fitting some compositional constraints that the composers impose. For example, I want to match this sound using this given orchestra, using only these dynamics, only use these playing styles, these kind of constraints. So mathematically speaking, this is a twofold problem. A part of it is a combinatorial optimization problem that is defined on the timbre. And the other part of it is a constraint solving problem defined on the symbols of musical writing, the variables of musical writing. So again, we see this connection between the symbolic space and the signal space in this project. I will give you more information on how this works because I thought it could be interesting that I give you more details before we go to the software. So guys, basically this talk would be something like, I don't know, I talk like half an hour using the slides and then we go to the tools, okay? So this is a combinatorial optimization problem. Why? Well, the easy way to see that is, suppose you have a target sound like a bell and you want to reconstruct this sound using instruments. And suppose that you are given an orchestra of 2 instruments like trumpet and clarinet. And suppose that each instrument can only play 2 notes, like the trumpet can play 2 notes and the clarinet can play 2 notes, like at a single dynamic, for example, piano. And then why it's a combinatorial problem? Because you make combinations of all these instruments and then you select the closest combination. For example, you take 1 note of the clarinet, 1 note of the trumpet, and then a second note of the clarinet, a second note on the trumpet, and so on. So yeah, basically you have 4 combinations in this case. Then what you do is just you compute a distance between each one of the combinations and the target sound. This is doable and it's easy. I mean, you can really find the best solution in this situation. So given the constraints, like you only can use 2 notes, you only can use 2 instruments, you only can use piano dynamics, then under these constraints, you make all the combinations that you can do, and then you pick up the best. The problem is that when you increase the size of this space, it becomes intractable. Like instead of having 2 instruments, suppose that, for example, the clarinet can play roughly 40 notes and the trumpet can play roughly 40 notes. But suppose that the clarinet can play at least 5 dynamics, like pianissimo, piano, mezzo forte, forte, fortissimo. And so the trumpet can. And then imagine that they can play legato and staccato, or they can play, I don't know, any other kind of playing styles. Then the number of combinations increase, like for example, I don't know, I would say 40 times 40 or something, times 5 times 2 or something like that. That's okay, that's still tractable. I can still make all the combinations and then rank them. But the point is that when you add other instruments, you add other playing styles, you add the whole orchestra, then the number of combinations becomes too big, on the order of 2 to the power of 30,000. So it's very, very huge number. So you cannot really compute all the combinations and rank them. So that's why we need something that is called optimization or minimization problem. So it's a heuristics that help you finding the best combinations in a large number of combinations. So it's a minimization problem. So you basically minimize the distance between the combinations and the target sound. But there is a catch. And the catch is that given that you have symbolic constraints, that you have, specifically strange constraints, like only using these combinations or not allowing these other combinations and so on, the problem is called a non-convex minimization problem. And that's why it is difficult. Like a convex that you see on the left is when the error of this problem is a smooth, parabola like that. And so you can really find easily the bottom of this, like the minimum error. But the non-convex that you see on the right is when you have more minima points. And these are, difficult for a machine to understand, like to understand when we really got to the absolute minimum of this problem, or if you should stop to some sort of local minimum that is not actually the best possible solution. And in fact, we are in this right case, right? So with assisted orchestration, we are somehow in a non-convex optimization problem in which we are not sure where is the real absolute minimum of our problem, because we are not allowed to compute all the possible combinations because there are too many. So we need to be smart. We need to find solutions that are somehow strategies that are somehow able to optimize this problem under these difficult constraints.
Hi,
So,
Carmen.
hello. Hi, Alessandro. Ciao. Nice to see you. So guys, thanks for joining me. So I hope it's fine, right? So are you okay with this discussion? Do you feel comfortable? I don't want to go into too much details, but I just want to give you a sort of feeling of the problem before, you know, going to the tools, to the real hands-on. Well, nonetheless, the general idea is we have the general structure of this problem is we have a target sound on the left. We have some constraints like musical constraints. We have a database of sounds, like in our case would be Studio Online, so SOL. And then you have a search engine that is, you know, doing basically two major things that I want to somehow discuss. One is the feature forecast, and the other one is the measure of dissimilarity. So the feature forecast is a step during the search that is basically, when you have a new combination, you need to forecast the features of this combination, because we cannot really compute the features for each combinations because the combination are, again, too many during the optimization. I will discuss that later in more detail. Just to give you a feeling that the fact that there are many problems in this search stage. And then the dissimilarity measure is a good, meaningful, perceptually reliable measure that tells you when two sounds are close or when two sounds are far. And this is not easy at all, guys, because timbre is very difficult. And I don't think we still have a good way to make a distance in the timbre space. Is an open question in my book. Well, nonetheless, when you're given a target, given symbolic constraints, given a sound database, you optimize and you get the solutions, and the solutions are scores. So I'd like to stress that the outcomes of these assisted orchestration tools are not sounds, are scores, so are symbolic outcomes. By, you know, side effect, we also generate sounds that you can listen to. You can evaluate by, you know, acoustic inspection, but the final point for me is generating a score, something that can be used by composers. Okay, so one word about these two things, the feature forecast and the dissimilarity. This is not at all important, but is I think it makes sense for me to kind of share these ideas so that you become more responsible when you use these tools and you know more what these things mean during the optimization. So you see on the left the sounds in the database that are described by features, D1, DK. And then you see that you make a random combination of these sounds, and you need to find the features of the combination. And in fact, you cannot compute them because you are not allowed to generate the combination and then compute the feature because it takes too much time during the optimization. So what we do is a forecast or a prediction of the combination. That's the first important problem. It's not easy to find a way to predict features that are non-linear features. So we don't really know how to predict them, but there are ideas. And then the second stage that you see on the right, you have the same features describing the target sounds, and then you compute a distance between these two. This is basically what the search engine does. So it generates combinations, it predicts the features, and then it compares this prediction with the real features of the target sound. I hope it makes sense. So this is somehow the best way I can describe this for the moment. The idea that the people that researched this problem at the beginning had was somehow this. We embed the sounds in a low-dimensional space, like using a few features that are meaningful for perception, like, for example, pitch, energy, or brightness, or bandwidth, these kind of features that are somehow meaningful to perception. And then what we use is a multi-objective optimization. A multi-objective optimization is something that minimizes jointly all the features. So we find the best solution given the pitch, the best solution given the energy, the best solution given the brightness, and so on. So basically, this would generate a set of best solutions called the Pareto front. The Pareto front is the set of solutions. Each one of them is the best given a feature. So this is an interesting approach, actually. And it was really interesting for composers because composers could, at the time, I'm referring to when I say at the time, I mean Orchidea, so it means 2007 and 8, basically. They can select this set of solutions, and then they can apply listening preferences. Like, for example, for me, it's more important the energy, so give preference to the energy. Or for me, it's more important the brightness, so give preference to the brightness. So they could actually interact with the search engine and can kind of somehow put biases on the search in order to maximize some specific features. This was the approach that has been taken by Grégoire Carpentier and Damien Tordieu in 2008 for Orchidea, and this, it was working very, very well. I thought I could give you a feeling of what is genetic optimization, that is the basics of their approach at the time. And I just want to give you two words that are important for us. One is crossover and the other one is mutation. So I thought I could tell you something about that. So why we use genetic optimization? Well, because as you remember, we cannot compute all the combinations of the sounds in a database and then rank them against the target sound. We just need to select some combinations. So genetic algorithms and evolutionary optimization is a way to generate selected combinations that are good enough for the problem. And it works like that. So you start with a number of combinations, like suppose you take 500 random combinations, and then you compute a fitness on this combination. So basically you rank them against the target. And then you take the best n of these random combinations, and then you apply genetic transformations that are called crossover and mutation. So crossover means that you take, given two different combinations, part of the one combination and part of the other combination, and you generate a new combination by mixing the two. And then mutation means that when you do this mix, you also alter a little bit the mix by a random factor that is called a mutation. And then what you do is you compute the fitness again, and you generate a new population, and then you optimize over and over again. In the long run, this has been shown to go towards the minima of your problem. If not the absolute minimum, at least very good local minima. So this is the basic idea that we have used since the very beginning of this approach. Basically, if I may, you don't want a greedy search in these kind of things. For example, the greedy search would be an algorithm that would maximize the distance in a greedy way. So like I take the best of the clarinets, I take the best of the violins, I take the best of the cellos, and then I put these together to make the best combination. It doesn't work. So it works to some extent, but it doesn't really work. It's like, when you are on Google Maps and you want to go from A to B, and so you go for the shortest path. Maybe this would imply to take a longer leg in your path instead of a shorter first before. So these kind of things. The heuristics, the evolutionary optimization in heuristics, was a very smart, clever way to generate a number of combinations in a very huge number of possible combinations and rank them using a specific distance. So again, these two words that we will see in the hands-on in a few minutes, crossover and mutation, are very important for us. So crossover is the amount of hybridization that you take from the best solutions of your batch, basically, and then you put together the two to generate new offsprings of these combinations. So this is sort of biologically inspired algorithm. But at the same time, mutation is a random probability, and basically increasing mutation, and this is important for us, affects the diversity of the solution. So the higher the mutation, the more diverse the solution. But there is a catch here. If you put too much mutation rate, then the solution will be random again. So you don't allow the algorithm to minimize, to find the best possible local minima for your problem. So mutation rate is a very important parameter that we will see in a moment. So as I was saying, these generated two very important tools. One was Orchidea, whose interface in MaxMSP was called Orchis. that has been used in many projects, among which, again, Speakings. And then the other one was Orchids. Orchids was the first, I don't know, I think, time-related orchestration tool. And then you see here in the interface that was using back, again, toolbox for showing the solution. So this was a very important milestone in this project, and we are about 2008 and 2013 respectively. And then this was the situation. I was, at the time, I was a user of these tools, and then I started being interested in developing this tool. And so that's when happened that we started Orchidea. So I go on, guys. If you are okay with that, we will. I will leave some time at the end for some questions. So I hope it's fine for you. Okay. So just to clarify how Orchidea works, I mean, how we are able to develop these. So this is a joint project between several institutions, among which IRCAM, of course, Haute École de Musique in Genève, and Berkeley, where I am now. Basically, IRCAM provided the basic infrastructure, the basic, cultural context of the project. HOM, or Haute École de Musique, provided the fundings and the pedagogic, infrastructure for the project. And Berkeley is now helping me as a professor to continue this work. So this is basically the interaction between three institutions. And this is a very interesting project because it affects different communities, and there are many different profiles that use these tools. So I thought I could give you a sort of overview on the milestones of this project. So the official beginning of Orchidea is 2017, where I decided to basically rewrite the code of the system orchestration. And at the end of 2017, I was able to have a sort of, I call it, at the time I was calling vanilla version. So it's a very simple version of orchestration that was somehow close to Orchidea, so no dynamic orchestration, but with different principles that we will see in a moment. Then in 2018, so in the mid of 2018, I added the temporal orchestration or the dynamic orchestration. And then at the end of that year, 2018, we had an interface in Max. It was a modular interface. So this was another major idea. Instead of having a monolithic interface like Orchids was at the time, I wanted to have a modular interface, like a language of the orchestration, so that each one could design, her or his own different workspace for orchestration. And then in 2019, I started adding new approaches for orchestration that I call semantic orchestration, that we will see in a second. And basically the two most important things at the time were the joint time target optimization that I will explain in a second, that is basically considering the optimization of the current target given the past of your optimizations. And then the connection models. Connection models are models to basically afterward to connect the solution in time. So basically giving a voicing of the orchestration. At the end of last year, we had another release in MaxMSP, and we had the first version of the standalone application that I will show you today. And basically in 2020, like a few months ago in April, I think, we released a third version of the Max Toolbox and the second version of the standalone applications. And then, of course, I had to also, I wanted to try to make some publication out of it in order to document the project. So, let me give a few key points of the current architecture, the current approach. As you may remember, in Orchidea, the idea was to use a low-dimensional embedding space with a multi-objective optimization. If you wish, in Orchidea, I do somehow the opposite. I take a high-dimensional embedding space, but a mono-objective optimization. But I add symbolic constraints in the cost function. So I don't know if you're interested in these kind of things, but the point is that I basically tried to increase the abstraction level, to think in a way that is more close to composers and less to sound analysis or engineers, if you see what I mean. So this is somehow a different approach, and it works, I mean, comparably well, I suppose. And on that, I built the infrastructure for the rest, for the dynamic optimization. So I will give you more information about that, and we will see more the details using the tools so that you can understand more. So another major difference is, instead of starting from random solutions, like as I was mentioning before, I decided to apply a greedy strategy to generate the beginning set of solutions that we want to optimize. So I used a pursuit strategy that I call stochastic pursuit strategy, that basically finds the closest best solutions and then starts generating a population with that. Then, of course, I wanted to try neural networks to improve this problem, and I developed a system to make the forecast or the prediction of the features using a neural network, namely an LSTM neural network. And then one major point of my work was the definition of a new way to evaluate the solutions in the temporal space. So I now use an asymmetric distance for evaluating the solutions, and this is exposed in the Max toolbox with the two variables called positive and negative penalizations. I will discuss a little bit later about this. And then the two things that I was mentioning, so the joint time frequency or time target optimization, that I call hysteresis of the orchestration. So basically, I put some weight on previous solutions so that the next solution will be somehow connected to them. And then finally, the temporal modeling. So the continuity model that I want to apply to the solutions in order to make a voicing of the orchestration. So I guess, yeah, so pictures somehow help. So the stages are, the overview of the system is like that. So we have a first stage of segmentation. So basically we cut a temporal signal into slices that are more or less complicated. Then we make a forecast using a neural network. Then we match this forecast using the stochastic matching pursuit and the evolutionary optimization by considering also the symbolic constraints during the optimization. And finally, we do a temporal modeling. So we just jointly optimize and we apply some policies for temporal connection. As you can see, between the match and the temporal modeling, there is a twofold arrow, meaning that I go back and forth between the optimization and temporal modeling to actually jointly optimize the solution across time. Yeah, I don't think we need that. So one word about the forecast. I don't think it's interesting, but I mean, maybe for some of you it is interesting, but I just wanted to show you that the idea of using a neural network actually improves by far the forecast. And this is important because this gives better solutions. So actually this is a major point of the new algorithm. So to recap, we have a sound. We compute a segmentation of this sound using a similarity matrix. This is a very standard approach in MIR to cut segments of sounds given a novelty measure. So you only cut when you see that the sound is new. And then we apply these two stages optimization with a stochastic pursuit at the beginning and an high-dimensional optimization. And then I put these solutions into a graph, and then I jointly optimize the path in the graph and the next target in the orchestration. So basically, you have a best path connection in time. So you try to connect the segments of your orchestration in order to minimize some sort of properties across time. For example, I want to keep the solutions as static as possible. So I want to avoid too much movement in voice leading of the orchestration. This is, of course, a choice. You can make your own choices. So just to wrap up about the temporal modeling. So basically, when we have solutions, now we have on the y-axis, we have the instruments, and then on the x-axis, we have time. So we have, this is a score, basically. when it happens that the solutions actually have the same instrument staying alive for more than one time point, then what happens is that the solution the optimizer just removes new onsets and try to increase the length of the previous onsets in order to maximize these some sort of connection in the orchestration. This is a principle of orchestration, that is very important for me, and it works. I mean, it's the very basic thing that you can do in orchestration. But to me, this is a difference between just having Orchidea or Orchis as instrumentation tools and Orchidea as an orchestration tool. Even if just for a little bit of that, just a little bit of that. I will tell you later what I think we should do for adding more orchestration to the orchestration tools by adding other, properties. The softwares. So what we have? So we have three things. One is the library. So Orchidea is a template C++ library that will be open source very soon, that you can use, and there is an interface that is a C++ interface that you can use to integrate in other projects. And this is for basically more research-oriented users. Then there is a Max package that I will show you in a while, that is made of tutorials and objects and abstractions. And this Max package is the most important deployment of Orchidea as for today. And then there is a standalone application that was meant to be an experimental kind of thing. So we didn't really invest that much yet. But since it's doing pretty well, and since I'm having very good feedbacks, I think we will improve these. We will add resources on this application. I will demonstrate this application as well. There is an extra thing. There are command line tools that you can use for orchestration. So basically, I use these tools myself for batch processing. When I want to process many samples, I want to process a database of targets, these kind of things, I will use the command line tools that I will also demonstrate a second. There is a connection between the command line tools and the standalone application, in that command line tools use a script, and the standalone application can also load the script. So basically, you can store the parameters of your orchestration and then batch process them using the command line tools. Here we go. Let's go to the real thing. So let's see what we have as tools. So the tutorials on the left. There are a number of tutorials. One is basically what I told you today. What is assisted orchestration? Why we do assisted orchestration? A little bit of the history of the project, and some rough ideas of what we saw today. And then we have tutorials on specific type of orchestrations, like the static orchestration and the dynamic orchestration. I assume that you don't know this tool for the moment, so I will go from scratch. And I think that the first choice you want to do is how close you want the solutions to be. Like, you want to make a mimetic solution, you want to copy the target, or you want to abstract somehow and make a more cathartic solution, if you wish, like something that is more abstract. This is a choice that you need to make. And basically, this goes to the choice between timbre and pitch. The close you preserve pitch, the solution will sound to the target somehow. But you need to trade off these with timbre. So you want to preserve the overall shape of your target sound, maybe compromising pitches. And so this is something that you can also decide in Orchidea, for example, by deciding which embedding features you use, such as the spectrum or the MFCCs. I'm not sure. So I assume that you know these features. If you want, we can discuss that later. So the more important object of the toolbox is the Orchidea.solve object. So basically, you see that there are three inlets here. One is for the database, and then one is for the orchestra, and then one is for the target. So these are the three things that you need to know to orchestrate: the database, the target sound, and the orchestra. As you can see, we provide a tiny sol abstraction so that you can, sorry? Okay, so let me go on. So this is the first, object that you want to familiarize. Of course, the objects have, all the objects have the help file. So we will go through this help file. The solve is the biggest object. So you will see many pages on top. By the way, I had people saying that they didn't see the tabs. And in fact, they are pretty, not so evident. But on the top of the page, you have tabs showing different things that you can do with these objects. So feel free to browse this help file. We will go a little bit there later. Then you see the first one was the tiny solve. So you basically load the tiny solve, and you will see in the max message box that you have loaded a number of instruments, that you have loaded a number of styles, that you have loaded a number of pitches, and so on. So you have some basic information of what you have in the database. Of course, we can ask more information to the database with specific object that I will show you. Then the second parameter is, of course, the orchestra. The orchestra depends on the database. So in the case of tiny sol or sol, the naming is as follows. So flute, oboe, clarinet, bassoon, horn, trumpet, and so on. Like basically the standard classical naming. So if you load the orchestra, you will see a message saying that the orchestra has been set. Of course, you can do many other things. You can, this kind of notation here with the slash means that these three instruments, like trombone with cap mute, or trombone with harmon mute, or trombone with straight mute, will be played by the single player. So this is when you want to use different instruments for a single player. Then you tell this in this way to Orchidea. So Orchidea will use one player, one instrument at a time, not all of them together, because there is a single person playing them. And of course, you have other things that you can tell to this object orchidea.solve, such as the styles that you want to use or the dynamics that you want to use. We will see a little bit of that later. Then you remember that this algorithm is still based on evolutionary optimization to some extent. So you still have these two important parameters that are the population size and the number of epochs of the optimization. The population size is the starting random set of solutions. So in this case, 300. And then the number of epochs is how many times you reiterate the evolutionary optimization by computing the fitness, generating offsprings, and then generating a new population. So in this case, 300 times. So 300 times 300 is good enough to have decent solutions. But of course, if you increase these two values, you will have better solutions, probably, but it will take more time. Again, you see that there are two important parameters, the crossover rate and the mutation rate. So the crossover rate, as we saw before, is roughly 80%. So meaning that you take from from two good solutions, you take 80% of one solution and 20% of the other to generate offsprings. And then mutation means that you will make a 0.01% of random mutation of these generated offspring. Again, mutation rate affects the diversity of solutions. So the higher, the more diverse, but if too high, then the solution will be random. These two values that you see here, 0.8 and 0.01, are good enough for starting. Just to be clear, I usually tend to not change too much the parameters. So I don't play too much with the parameters. And I'm fine, I usually have good enough solutions for me. No, let's give it a run. So I will just press this button, and if it works, we'll see in a second. So you see this. Okay, can you hear the solution, guys?
Yes.
Okay, is it? I think, let me try again. Yeah, so the pitch changed. Now it's correct. So there was a sampling rate problem. So now you see, do you hear the solution yet, right?
Yes. Yeah.
Okay, so basically we generated the solution. We have the solution that we can play. So it's stored in a buffer. So you can play the solution here. You can also check the target that is stored in a buffer. In this case, it was just another bell. And but most important, you can see the solution in a back roll object. So you see the instruments with absolute durations in second, and all the parameters of the orchestration, or the dynamics and the sense of the intonation. Of course, now you see this spinning ball because there is a parameter called parallel that is set to off. And this is useful for the sake of a tutorial, but in your real work, you may want to have this parallel set to 1, so on, so that the orchestration doesn't block max MSP when you orchestrate. For example, in a real-time setting, when you are orchestrating for a concert or something, you may want to have these to 1. Of course, if you change these two, like I increase the mutation rate and I increase the and I decrease the crossover rate, this would somehow give different results to some extent. Still okay, still acceptable, but different from the previous results. So the point is that now the mutation rate is higher, so each one will trigger the orchestration. There will be a chance that the solution will be somehow different. To some extent, this is a very easy orchestration target, so it works pretty well in this situation. Okay. Now, I want to focus on two more parameters for this Orchidea.solve object. One is the sparsity parameter. Sparsity is a way that we use to ask Orchidea to either use all the instruments or a selection of the instruments of your orchestra. So when you define the orchestra, maybe you don't need all the instruments at each time. For example, suppose you have a very high-pitched sound and you have a double bass, then maybe the double bass will not be helpful in orchestrating this sound. So if you say that the sparsity is 0, so Orchidea is asked to use all the orchestra. That can be too much, for example. If you say that the sparsity is something like a probability between 0 and 1, then you will drop instruments and the solution will be more sparse. So let's see a dense solution. So the target in this case was a clarinet note, A3. So you see that there is, of course, it found the partials of the clarinet, like the A and the E, and all the instruments are on in this solution, but it feels too much E for me. So if you allow some sparsity, now you have less instruments, among which, of course, a clarinet. So it found a clarinet as a target sound. And you see more, you hear more A than E in this case. So sparsity is better. So for example, I tend to use a higher sparsity when I have single notes used as targets. I tend to use lower sparsity when I have dense sounds, like orchestral sounds, used as targets. Now, the second parameter that I want to show you is the partial filtering. This is a very extremely important parameter. I guess I would, let me take this slide here. So what is partial filtering? Basically, when you have a target sound, the first step we do in the orchestration is we analyze the target sound using the FFT. And we compute the spectral envelope of this sound. You see here, for example, that there are peaks in the spectral envelope that corresponds to specific notes. In this case, A3, A4, E4, and so on. Then the partial filtering is a threshold that you put on this envelope, saying that you only consider for orchestration the peaks that are above this threshold. In this case, we don't consider the last peak. So since each peak, each partial correspond to a note, this will filter the database and will use only files that have this note as a reference note. So for example, in this case, we'll select the oboe A4, the clarinet E4, but we will not select the clarinet G4, G sharp 4, or the oboe D5, and so on. So basically, increasing the partial filtering, so suppose you put this value to 1, then you will only take the highest partial, the first partial, in this case, A3. If you put this value to 0, then you will take any partial, so there will be no filtering in the partials. If you put something, I don't know, like 0.3 or 0.4, 0.2, you take the best, the strongest partials of your target sounds to drive orchestration. So this is a very important parameter for the bias, timbre, pitch. If you increase this value, you give bias to pitch. If you decrease this value, you give a bias to the timbre. So again, depending on what you want to do, if you want to orchestrate sounds and you want to preserve the pitch content as more as you can, then you should increase to some extent this parameter. Otherwise, you should decrease this value. So in this case, I will give you an example. It's a kind of a goofy example, but so we have a symphonic chord taken by from Beethoven, and then we use a high value for partial filtering. This is very high. 0.4 is pretty high. I usually stay around 0.2. And then we don't use this value, so we set it to 0. Okay, so the first solution will be more pitched, and the second solution will be less pitched. Let's see. So you recognize the code, you recognize the notes. If we run that without the partial filtering, so these sounds contain bad pitches, but the spectral content is brighter, and that is closer to the real target. If you play this target, you will see that this is somehow brighter. And by the way, these targets, the Beethoven, the clarinet, and so on, are included into the Max toolbox. Okay, so these two are very important parameters. So the sparsity and the partial filtering. But let's go ahead and see what happens in the context of a dynamic orchestration. So if you go to tutorial number 2, you will see that we explain a little bit how it works, dynamic orchestration. So we basically do an analysis, an on-set analysis of a target sound. In this case, we see even mistakes that the algorithm does for the analysis. And basically, the two most important things that you want to use for these analyses are the novelty value, the threshold that says how much new sound you want to consider to make a new onset, and the time set, the time gate set, saying that you don't allow targets or segments that are too close to each other. This is a very important concern for playability. If you have onsets that are too close, like a few milliseconds apart, maybe you will generate a score that is not really playable by an orchestra. So this is also something that you need to consider depending on how you want to use this tool. I have a user, so I've discussed with users of Orchidea that are not really interested in using Orchidea to generate scores. They only are interested in generating sounds. So in this case, this is not a concern at all. So let's run a dynamic orchestration. So in this case, you see a bunch of default parameters. Just to spot few ones, you see that I decreased the number of epochs and the population size to 100, so it's less precise orchestration. But I increased the partial filtering pretty high to 0.4. And I have a little bit of sparsity. So this solution will be dense, but not using the whole orchestra by default. So let's see what happens. Again, you will see a rolling spinning ball here. Let's wait a second. So it takes a little bit more because it now orchestrates a dynamic sound. In this case, I think it will be like 7 or 8 onsets that have been found. So let's play the solutions. So you can use these two players to compare the targets and the solution, but you see it works fairly okay. So as you can see, I was mentioning Orchidea does not depend on BAC because in fact it outputs a dictionary, a Max dictionary as the solution. So you can actually browse and use this information without having BAC. Of course, the BAC is a good way to have an immediate feeling of the quality of your solutions. Of course, changing these two parameters that are the onset threshold, so the novelty threshold, and the onset time gate, you will affect the way Orchidea will segment your sound. By the way, you can use your own segmentation algorithm and ask Orchidea to follow your segment. So this is something that is documented in the orchidea.solve help file. Okay, then let me play another example. In this case, we have a sound that has not been generated by an orchestra as the other case, and we have something more strange. It's taking a little bit of time. You still there, guys?
Yes.
Okay. So, by the way, I noticed that Zoom affects very much the performance of my computer. So now the target being this, and the solution being this. So it's kind of a strange, funny thing. Okay. So, but just to show you that depending on the target, you can actually tweak the orchestration to do more or less abstract orchestration, if you wish. Now, before we go to the standalone, I want to show you a couple of things more. One is the third tutorial about how you browse the solutions. Because as you may remember, Orchidea generates a bunch of solutions per target. So we have a way, we put in place a way to browse these solutions in an efficient way, even for dynamic solutions. So it will take a little bit of time, but I think it makes sense for me to show you this. Then I want to show you a couple of things more on the Max toolbox, but I want to focus again on the GUI. So in this case, I orchestrate a sound. It takes a little bit of time because you see here that there is a parameter called max export 200, meaning that I save physically all the 200 solutions that we have at the end of the optimization. This is usually not needed because usually you take the 10 best solutions, but I do that explicitly to show you how you can browse a large number of solutions using the infrastructure that we put in place in the Max toolbox. And this infrastructure actually depends on data, the data objects that are that has been developed by Daniele Ghisi and Andrea Agostini. So let's take a second and we wait for this. By the way, I will, so I don't know, I'm supposed to close at 11, but I will be free. So if you want to stay like 10 minutes more, it will be fine for me. And we can have some time for questions if you have any questions, or you just feel free to drop me an email later on. Okay, so we have the solution orchestrated. Then what we do is just we set up a database or data.base object. And then if it works, we should be able to browse at least, you know, you see that I just scroll through the number of solutions and then we see the solutions that are shown here in the back.roll. By the way, the 200 solutions are all different. So even if for a single node, but they are not equal. Now what you do is we describe the solutions using low dimensional features like they were doing on Orchidea. For example, in this case, the spectral centroid and the spectral skewness that are somehow related to perceptual properties, for example, brightness. And then we analyze all the 200 solution, so it will take a little bit of time again, but this is useful to then make a 2D space, centroid versus skewness, where we actually plot the solution and then we can navigate the space by features. And this will be much more meaningful when you have too many solutions to browse. So these examples, yeah, I think we are okay. Then we should be fine. Here we go. Now I put all the solutions in this 2D space in which we have centroid versus skewness. When I go when I go on each point, you will see that you play the solution and you see the solution on the right. And you see that the more I proceed to the right, the brighter the solution. so on. Then I think it makes sense for me to show you something that is, it will take a little bit more of time, but is really important, and is how we browse multiple solutions per time point. So when you have a dynamic target, you will generate a number of solutions per time point, and then you want to browse all of them in a single way. So that's what we do here. So it will generate now a bunch of solutions. It will compute the features automatically, and then we will have the solutions plotted into, you see here, now this is in parallel mode, so I can move around, and you see that we are optimizing the segments. We have 300 segments. So I think this solution has, I'm not sure how many, so yeah, we will take a little bit of time because we will have roughly 30 segments, 300 solutions, 300 epochs per segment. So we are at number 3 now. So it will take a little bit of time, but I think it makes sense because I want to show you something. While it computes, I go quickly on the 4th tutorial, okay? The 4th tutorial is meant to show you what you can do by querying the database. So for example, you want to ask to your database which kind of instruments you have, which kind of playing styles, which kind of dynamics you have. Or you want to actually find all the flutes in your database, or all the instruments that have a dynamics of pianissimo, or for example, all the flutes in the 4th octave, or all the flutes that play a C sharp, and so on. And then we can do something that's even more complicated. Like, for example, we retrieve all the violins, and then we only take the violins whose pitch is lower than 60 in MIDI. So these kind of things, these kind of queries, we can do using the object orchidea.db query. So I don't do that because I think I want to wait that this thing finishes, but I will show you this quickly. Okay, it will take a little bit of time. So if you are okay in staying 10 minutes more, I think I can even show you the object orchidea.db.gen. That is the object that you want to use to generate your own database. So instead of using Sol or using provided data sets, you can generate your own database. So let's see, I think it should work without creating any problem. So for example, if I load these, does it work? Yeah, my laptop is somehow tired. Okay, now I think we loaded in an independent object called orchidea.db.query the database. So we show here in the window, I can retrieve the instruments. For example, these instruments are the ones that are present in this database, or I can ask the styles, in this case only ordinario, or I can ask the dynamics. These are the dynamics that you can find. Or for example, what I can do is just, I can retrieve all the flutes here. These are the files that are flutes in the database, or all the piano dynamics. And this is the set of files that are dynamics corresponding to the dynamics, if I understand well. Then the other thing is, sorry? So let me go ahead. So for example, you can actually ask for the flutes that have a C sharp, and you browse them, or for all the flutes in the 4th octave. Or you can actually, for example, say, give me all the violins let's see how much time does it take. Oops, yes. I think my system is under stress at this point. Yeah, I think it's not okay. Yeah, I'm not sure what's happening here, guys. I think is too much work. Let's wait a second. I hope it will recover. I'm not sure at this point. So Max is stuck. That's the demo effect, right? No, here we go. It recovered. So let's go back where I was. So now I think you can even say I filter and I remove all the values that are above MIDI note 60. So these kind of things is the queries that you can do on your database. So it makes sense, especially when the database is big, like the full Sol, to be able to retrieve information about your database. Now, if things were okay, here we go. Now we have time points on the x-axis and solutions on the y-axis. So at this point here, or at this point here, so this is a nice way to browse the solutions in time, right? So, and then you can make your own path, selecting the ones that you like best. I think it made sense for me to show you these things that are really powerful, in my opinion. Then you will be able to. So there are 2 extra tutorials about how you build your own workspace in the Orchidea sense, and how you work with scores. I encourage you to have a look to these tutorials, because they will, give you a feeling on how much work you need to be able to make a powerful somehow workspace. And I think if Hans is also listening, Hans, yes, he is here. So Hans is is a very advanced user of Orchidea, and when I see his own workspace, I basically faint out. It's very complicated. It makes a lot of things together. So that's nice. That's the point of Orchidea for me. Like the fact that you can use your own, you can make your own language for orchestration, and then customize it to your needs. And so this tutorial guides you through this process of making your own workspace. And the last one is about scores, like how I can generate scores. And this is maybe more a tutorial about how you use back, how you want to quantize the scores, how you want to replace the instruments, and how you change the pitches and alter the tuning and this kind of information. And you basically generate a real score and so on. So this is more somehow related to back. So I also encourage you to have a look to the back tutorials that are very, very well done by Daniele. So, well, okay, this is somehow the overview that I wanted to give you for the toolbox. There's an extra thing that I want to show you. So if we go, so let me close a little bit of things, because my system is really tired now. As I was mentioning, I don't know why, but Zoom takes a lot of resources from my computer. So, yeah, I had many instances open. I'm closing a little bit of things here. Okay, here we go. Now, if we go to the objects, okay, so the dbgen object is an important one, because is the one you use to make your own database. So let me see if I can give you an example of this. So this is a folder called targets, okay? These are actually the targets that I ship with Orchidea. But you can use this as a database, just for the sake of discussion. So I just drop the folder here, and you see that there is an analysis going on, and you see the files that have been being analyzed with default parameters, but you can change them. And the output is indeed a file called targets, as the folder that you drop, .spectrum.db. So this is the analysis. And this is what you need to use Orchidea. You will need to tell Orchidea, we'll see in a second, the database and the files. The database is needed for optimization. The files are needed for sound rendering. So without the files, Orchidea will not be able to just play out a solution, okay? So this is very simple, and you have some features that you can change and choose from, and then other parameters that you can actually tweak and change, okay? So this is the dbgen object. And the other one I think I was mentioning is the Orchidea.solve. So feel free to check the things. For example, you can use inputs in Orchidea like files, or you can use buffers, max buffers as inputs. This is more for real-time kind of thing. And then you can use manual segmentation. So you input a segment list as, you know, a list of values, and then this will be the segment that will be used by Orchidea. And then I think the page that you want to check is the search page. So the parameter of the search. Like we saw population size, population epochs, the sparsity, the mutation rate, and so on. And so these two, for example, these are the negative and positive penalization. So let me give you a second, an overview of these two parameters here. So the penalization is done as follows. So basically, suppose you have the target being the spectrum in black, and the combination, the current solution that we are now evaluating in blue. So suppose that you make a difference between the target and the solution, and then you weight differently the case in which the target overshoot the solution from cases in which the target undershoot the solution. So in the case in which the target is below the solution, I call it positive case. I just make the difference between the two, and I weigh this by a coefficient called positive penalization. And then when the solution overshoots the target, then I call it negative solution. And so it's a factor that is used called negative penalization. And I take the absolute value of the difference of these two. This is a very simplified version of the cost function. The real cost function is much more complicated because we have time into account, we have symbolic constraints and so on. But just to give you a feeling of what these two coefficients do. In other words, if you penalize more the negative cases, you will have more darker solutions in which Orchidea will not try to overshoot the target. If you ask more positive penalization, then Orchidea will probably try to overshoot the target, and so you will have brighter solutions, but you may hear spurious notes that are not in the target or something like that, if it makes sense. So these two parameters are positive and negative penalization. I keep a ratio between the two that is roughly 10 or more than 10. So I increase the negative penalization more than the positive penalization. But guys, I usually don't touch these two. So they are fine for me. I basically don't touch them so much, okay? Okay, so I think it makes sense for me to stop here for Max, and let's go to the standalone application 1 second before we want to wrap up a little bit. So the standalone application is experimental for the moment, so it's not so developed as the Max toolbox, but well, nonetheless it works. And so the thing you do is just when you so the first thing you want to do is just you go to the setting and you select the database, right? So you see the DB file that we just generated and the folder in which the files, the sound files are contained. This is what you really need to start. That's the first step you need to do. So select the database and select the files. When you did that, you make a new project in this case, and you select the orchestra you want to use. I just do a random selection, whatever. And so you have these instruments that are here now, you know. And then the easy way to do that is I just drop the target. So I just, I don't know, take the clarinet, I drop it on the application. And then, you know, this is for the parameters. The first thing I do is just deciding if this will be a dynamic or a static orchestration. Let's suppose it's a static. So I set the novelty value, the novelty threshold to 1, meaning static. You see that this is, you know, when I go to 1, it says static here. And then basically that's it. I just orchestrate. Here we go. So if we take another target, for example, I don't know, this gong here. Let's say that we go static again, and then I just orchestrate. Of course, you can move the target, you can do any kind of editing thing. So the main idea behind the standalone application was to enforce time in the composition of solutions, so you can make your own score. And then let's give it a try with a simple, I don't know, dynamic target. So this will be, yeah, let's say we try. So I don't change the threshold. I stick with these two values to see what happens. I select it, will take a little bit more of time because it also will generate a number of orchestrations. And you see the progress bar here going towards the target.
Just while it progresses, Carmine, this is Vincent speaking. Can I ask you a question?
Sure, go ahead.
Yeah, so the question is about the duration of the target versus the duration of the sound samples in your database. How diverse are the durations in the database, and are they extended by computational means, or are we tied down to specific durations?
So that's a good question, thank you. So for the moment, the idea that, so the solution we have is, if the target is shorter than the sample, then we fade out the sample basically. So we cut the sample to the length of the target. If the target is longer than the sample, we'll fill in with zeros. So there is no way to extend the length of the samples. But this is not completely right in the sense that, you know that we retune the solutions. By retuning the solutions, we actually can affect the time length of the samples. So it's just a matter of choice. And for the moment, the solution was not to alter the length, extending the length from the samples. But this is something that I could consider adding, like a flag, for example, saying stretch the sample to match the length of the given target. Does it answer your question?
Yes, thank you. Yeah, I was supposing that on some, harp sounds or guitar sounds, obviously you can't extend the sustain much longer than what the physics of the instrument affords. But if you have a wind instrument or a bowed string, duration is yet another parameter of the orchestration.
Definitely. So in fact, this is a very nice question. The point is that it's not easy to choose the right way to do that. Like extending a sound like a guitar sound or something is not really correct because you alter very much the onset, you alter very much the nature of the sound. But as you point out, for some sounds it could make sense. But then there are concerns regarding the playability of the thing. For example, if it's a wind instrument, then you need to have a player that is able to play the sample, and so you cannot extend to like 30 seconds or something.
Yeah.
So this is like playability is an issue because again, I stress again this thing. Orchidea is meant to generate scores, not sounds, right? So the sound is sort of a side effect to evaluate quickly the solution, but in the end, what we want to have is the score. But still, this is a good question. Like, in fact, as you may understand, the way I use it says there is a phase vocoder that synthesizes the sound. So I could easily change the length of the samples, matching the length of the target sound. But this would imply some sort of decisions about the playability, about the nature of the sound, and so on.
Yep.
Does it make sense?
Yes, thank you.
Okay, thank you very much. So I think it's done here. Let me see if I manage. So I had, there's a funny thing. So I had some users of the standalone application saying that they didn't know how to use a target on this tool. Well, the easy way is just to drop the target on the score. That's it. That's the only thing you need to do. But I think maybe this is not so easy sometimes. So I'm still waiting for this to finish. I don't know what's happening now. I think it takes time here we go. So this is the solution generated. I can zoom in a little bit now. Okay.
Whoa.
So you see, you see, guys, that there are sounds that extends beyond the onset. This is the continuity model that works. So in this case, we have sounds that are overlapping with other onsets, and this gives this sort of continuity feeling that you have in an orchestration. Of course, this is a very rudimentary process at the moment, so we will increase. I hope I will be able to improve this thing. So by the way, all of this is movable. You can copy, paste, and do any kind of sort of thing. And when you are done, you can either export the sound generation or the music XML equivalent of this, and then you open these into your favorite editor, and then you edit this solution. So this is a sort of time-based approach to orchestration that could make sense for me as a composer. So just to quickly show the parameters, the optimization has some parameters. And again, I see the mutation rate now is called diversity here to simplify the idea. And sparsity, these are the two that we discussed. And then instead of having the number of epochs and the solution, I just decided to have three presets: low, medium, and high quality, the high being more slow in the computation. And then you can also apply some filters. You can say which kind of dynamics you want to use, which kind of playing style. In this case, I use the full sol, so you see many playing styles, and which kind of other things you want to apply as filters for your orchestration. And of course, you can, so the idea is that I wanted to use this also as a sort of digital audio workstation for orchestrations. So you can eventually set this target to be played as the target, not the orchestration, and you can make mixed music, like, you know, instrument plus sounds, these kind of things. And then, of course, you can export these files so that you generate your own music. 1 minute more, if I may. So I just wanted to show you these standalone applications. So the standalone application, there are a bunch of applications that you can download. You can still find them in the website, the web page, and command line tools in this case. And of course, you have dbgen, that is the generation, dbquery, that is the query on the thing, but the most important is the orchestrate. So basically, to orchestrate, you just use specify the target. For example, I don't know, the clarinet, and then you specify a script that is, in this case, static orchestration. It does the orchestration, and then what you get is, so this is now searching. What you get is a number of files, among which connection.wav and connection.txt that are the solutions. So connection.txt is the symbolic representation of the solution. It's a list of lists, basically. So you see, in this case, segment 0, solution 1, note, beginning, flute, instruments, and so on, with tuning, cents, 17, 15, and so on. And you can play this solution. And the interesting thing is, for me, is that if I open, so this is the script. So the script is a simple configuration script in which you have access to all the parameters of the orchestration, okay, you see here. But the interesting thing for me is that you can actually use this script here, solve from script. You actually load the script in the interface. So basically, what I'm saying is that I would, I don't know, probably test the parameters using a command line in a batch kind of fashion. And then when I find the best, I use these to orchestrate my own things using the GUI application to interact with the solutions in a more proper way. Okay, guys, so let me wrap up 1 second, and then, I have in mind some steps for the future, depending on how things go. Well, so you see that this approach that we call the classical approach is a mimetic approach. Like basically, I copy the sound of the target, and we actually have no major assumptions on the style of the orchestrations. We just, our optimization is done on the features of the sound. But what I call the morphologic approach is something that I would like to try in the future, and I'm discussing with few composers that work on this project about this. And the idea would be to actually assign morphologies to the target sound, so decode morphologies, and then copy the morphologies in order to somehow have some sort of style-related assumptions on the sounds. So if it, I don't know if it makes sense, but basically the idea is to have an embedding space in which you have time, frequency, morphology, and texture, and make a very large dictionary of these morphologies, and then match the best atoms of this dictionary, and then implement these morphologies for the right solution. So I'm working on that. I think it's interesting, and it will be more musical. It will be more orchestration than instrumentation, but still it's something that is ongoing. And then, of course, there is another step would be using neural networks. So I just submitted to Izmir a sort of experiment in which we use a couple of models, among which a convolutional network with an LSTM unit in between, to orchestrate, and we got decent results. So there are some ideas in which how you can decode information from the neural network to the symbolic domain of orchestration, and we found some interesting ideas. This is just a preliminary attempt, so it's not doing as well as Orchidea, but I think it's interesting to keep an eye to these technologies in order to see how these would work for our problem. Okay, so there are a few papers that I'd like to point out. There is a major thing that I'm trying to do since a couple of months now, but I don't manage to finish. That is a paper that I'm planning to submit by this June, in which I somehow give an overview on the assisted orchestration problem as I see it, and I present Orchidea. I introduce Orchidea officially. But there are previous papers already published, like this one with Marcelo Caetano about biologically inspired models for assisted orchestration that will appear in a book called Handbook of Artificial Intelligence for Music, edited by Eduardo Miranda. And then there are other papers, one with John Gillick from Berkeley and David Bamman, that is the model that we implement for forecasting the features, so implementing this idea of prediction of features. And then there are other papers in which I talk about Orchidea to some extent. So I will leave these PDF somewhere so you can download and eventually check the papers. I think I am done. I'd like to thank you very much for your time. And I'd like to dedicate this talk and this work to Eric Dobrès, that is one of the figures that has been a central figure in the development of this work since the very beginning. He left us a couple of years ago. So I think it makes sense for me to thank him as well. So thank you very much for your time, guys.
Thank you. Thank you, Carmen. Bravo.
Thank
Bravo.
you.
Goodbye.